Welcome to Ready to Derive. In this video, we're going to revisit position, velocity, and acceleration, this time using integrals. So we met this once before when we did derivatives, and now we are going to find ways in which it's so much more powerful now that we have the tool of integration. So you will recall that for position, we used s of t, but sometimes we used x of t, y of t, h of t, t representing time, our independent variable. And we learned back in the day that velocity was just the derivative of position. Well, if that's true, then the inverse must be true, which is that if we want to find position and we know velocity, we just need the antiderivative of it. Similarly, acceleration was the derivative of velocity, which would be the second derivative of position. But if we had acceleration, we wanted to find velocity, then all we need to do is take the antiderivative. So with our integrals in hand now, we will be able to tackle much more sophisticated problems that relate to position, velocity, and acceleration. So let's get started. So we're going to kick this off with a real-world practice problem. So a potato is launched vertically into the air with initial velocity of 48 feet per second from a height of 6 feet. And we are going to find the maximum height reached by the potato using only calculus. So you may have seen this type of problem in physics before, and what you're about to see now is kind of how the formulas that you use in physics are derived. So yay, calculus. Here we go. So velocity is the antiderivative of acceleration, and we know that on the surface of the Earth, the acceleration in feet per second squared is negative 32. If it was meters per second squared, it's negative 9.8. So let's take the antiderivative of negative 32 as a constant. So we get negative 32 plus, don't forget, c. And here we have a piece of information. We need to find c. So to find c, we have to know some fact about velocity. And we have that up here, which is that the initial velocity, i.e. v of 0, is equal to 48. So that allows us to plug in 48 here. And of course, t is 0. And it gives us that c is 48. And now we have an equation for the velocity of this potato. So now, since we want to find the height, we have to therefore find the antiderivative of velocity. So let's do this again. So negative 32t plus 48 goes here. And then if we take this antiderivative, we'll get negative 16t squared plus 48t plus another constant. Well, we might as well just call that c again. It's a different c, but why not? And then to find c, again, we have to use some condition that we have, which is that the initial height, so h of 0, equals 6. So we just plug 6 in here and 0 in for t, which makes those terms disappear, and we get c equals 6. So now we have a formula for the height of this potato. And if we want to find the maximum height, well, we have to recall back to earlier material. That will occur when the velocity is equal to 0. So let's take the velocity formula, set it equal to 0, and if you solve that, you'll get that the maximum height occurs at 1.5 seconds. And then the last thing we have to do is take 1.5 and plug it in for t in our height formula. And h of 1.5, I'll let you do that, plug that in. You should get out 42. So we can conclude that the potato reaches a maximum height of 42 feet. And that occurs at 1.5 seconds. Now, before we move on, you might have seen this formula before. Like I said, for the height, negative 16 is really half the acceleration due to gravity. So that constant will change depending on what planet you are doing this. So hold on, one thing, that doesn't look like a g, but I'll make that. That's half gt squared plus the 48 is the initial velocity, v0t, and the 6 is the initial height, often referred to as h0. So this might be a formula that you are familiar with. We need need to do a quick recap of the difference between displacement and distance. We learned about this earlier on in the unit on differentiation regarding particle motion, but so let's revisit this. So say here's a number line. We have a particle moving back and forth along this number line. And let's say that it starts off here. So its initial position is at 3, and it goes to the right and then moves to the left and ends up with its final position being at -4. If we recall, displacement really doesn't care about what happens in between. It's just your final position minus your initial. So -4 minus 3, your displacement would be 7, negative indicating to the left, and that's shown by this white arrow here. So relative to where you started, you're now 7 units to the left of there. In contrast, we are going to look at distance. So now the distance has to take into account this kind of turnaround point. So we could call that like the interim point and see, so that happens at a position of 8. So if you want to think about the distance traveled, you have to think, well, what's the distance traveled along the green arrow? And that would be 8 minus 3. And then we would have to add to that the distance traveled in red. And we'll see that let's see, your final position is -4. The interim position is -8. And so 8 minus 5 would be 3, plus -4 minus 8 would be -12. But realize we don't want to have negatives when we're dealing with distance. So what we did in the past is we just stuck absolute values on there just to be safe, because we never know which displacement, because these are both displacement calculations. We don't know which displacement will be negative, so to be safe we do that, and the distance covered is 17. So let's formalize this. So if you recall the displacement formula, now A and B are time values, by the way, not number line values. So A and B are time values. So the displacement over that time value, where it's assumed that B is bigger than A, is just the position SB, your final position, minus your initial position SA. In contrast, distance traveled over that interval, you have to kind of break it up. And you have to break it up depending on where you turn around. So if we calculate, so the time at which you turn around to be T1, then you would do the displacement between A and T1 and then T1 and B. And if you turned around more than that, you'd have to kind of add more calculations to allow for every turnaround point. So here we go though. But what if we don't have a formula for S of t, as we did when we first encountered particle motion, and instead we only have a formula for the velocity? Well, that's where antiderivatives are going to come into use again. Now we're going to come up with the formulas for displacement and distance when we're given only the velocity of a particle. So we can't do this without our favorite theorem, the FTC part 2. I'm going to write it in reverse. So, and you'll see why in a moment. So f of b minus f of a, that will be the area under the derivative of that function, which would be indicated by that. So if we want to think about displacement of AB, well, if we wanted displacement, then instead of f, we want s there. So that will give us s of b minus s of a, that's the displacement. According to the FTC, if I replace f prime, we can make that s prime. And while we're at it, we are dealing with t, so let's just replace all of the x with t. Well, what is s prime t? What is the derivative of the position function? It's just the velocity. So the area under the velocity curve from A to B will give us the displacement. Now, how does that work? Well, here's a velocity curve, and notice that the velocity is positive until 2, and then afterwards it's negative. So it's like what we saw before. This particle is moving to the right and then to the left, and if we're interested in the displacement, we're interested in the area from the green area there and the red area. So let's say that the green area is 2 units, positive 2, and that the red area is half, but we know that we're going to write it as negative 1/2. Then we know that the displacement, if we could have calculated those areas, would just be 2 minus 0.5, which is 1.5 units to the right. Now let's see how we adapt this to deal with distance. So if we would like the distance over a to b, we don't want that 0.5, that negative 0.5 to be negative. We would like it to be positive. So here's a genius way we do this, is we actually take the absolute value of the velocity function and find the area from a to b. So let's have a look at this. So what we do is we take that negative portion, we absolute value it, becomes positive, and then the area that we're interested in becomes positive also. So this is 2. Now this becomes 0.5 according to our calculations, and the distance traveled would be 2 plus 0.5, which would be 2.5. So let's practice using these two formulas. We have a particle moving along the x-axis with velocity given, and over the interval 0 to 4, we would like to find the displacement of the particle. So let's call up the formula and then let's dive right in. So the velocity formula for this function, a particle, is 6 minus 2t dt. So we take the antiderivative, we get 6t minus t squared. From 0 to 4, we plug in 4 first, and then we plug in 0, which will just give 0. And the final answer, let's see, 24 minus 16 is 8. So the displacement, the particle moves 8 units to the right. Now for the distance, well, it's this formula with the absolute value, but this is not easy. It's actually not useful to calculate this by hand. This type of problem usually allows you to use the calculator. So we're going to teach you how to do this on the calculator. So first of all, what you do is you go to the math menu and you choose option 9, which says fn int. And when you do that, you will get this expression in the home screen. And then you just have to put in the relevant information. But the thing is that, so you put the 0 and the 4 there. The thing is that you need to get absolute value in there. We see where that black rectangle is, you need absolute value. And that can be found in the math menu also, but you have to scroll over 1 to number, NUM, and then choose 1, which is absolute value. And then that can get in there. Notice that I've used x instead of t because it's just the most convenient variable to use. It doesn't matter as long as they match, so x dx, and the answer comes out to be 10. So we found that the distance traveled is 10, the displacement is 8 over the same interval, which is always indicative, since they're not equal, indicative of the fact that this particle must have turned around in the interim. So we're going to revisit that practice 2 part B without a calculator because it was a pretty easy velocity function, and it's likely that it could occur in a non-calculated section on the test. So we need the distance the particle travels over 0 to 4. What we really need to find out is where this particle turns around, because then we can calculate separate displacement calculations. So the particle turn around when the velocity is 0, and that gives us 6 equals 2t, which gives us at 3 seconds it turns around. So we're going to have to consider the displacement in those 2 sections. So let's call up this. So that will be the area under the curve from 3 to 4 under the velocity function, and then from 0 to 3. So let's just quickly calculate these. So there's the antiderivative from 3 to 4, and from 0 to 3. And I'll let you do those calculations to save a bit of time, but this will come out to be -1. And from 0 to 3 will be 9. But we mustn't forget, right? I left them off at the just before, but we mustn't forget that we're really taking the absolute value of everything. So that would come out to be 10. So the distance traveled is 10 units, as we confirmed using the calculator in the previous slide. And I just want you to see a visual of this because it's kind of cool. It makes sense because here we go. This is 3 seconds right here. So we can see the velocity curve goes from positive to negative. And we can also see that the area, so we could have done this geometrically by just working out areas, but it's nice to see the connection. That would be half base times height. The height is, 6. and that comes out to be 9. And then we're interested to up until 4 seconds, which is right here. And that area under there is a half. The base is 1, and the height, you could think of it as like, you know, because it's -2, that'll help you to realize that that area would be -1. So yes, the distance traveled is 10, and we can also see, because 9 take away 1, that the displacement would have been 8 units, as we discovered in the previous slide. So in this practice problem, we are going to actually work on finding the position of a particle given some information about its position at another time. So same velocity formula, just for simplicity. This is a little reminiscent of the introductory potato problem, where we were given its initial height and its initial velocity. So same kind of idea. What we're going to do is use indefinite integrals. We're going to find the actual equation for s of t and work with that. So here is the antiderivative formula. The position will be the antiderivative of the velocity. And in this case, we have 6 minus 2t dt. So we'll take the antiderivative, and that would be 6t minus t squared. Don't forget the constant, and we can call that our position function. Now we use the fact that, let's see over here, we have an initial, well, not initial, but we have a point that we know that this must pass through. So we have that s of 2 equals 4. So let's plug that in to solve for c. So 6 times 2 minus 2 squared plus c. If you solve that, rearrange it, you will get c equals -4. So our formula is, our final formula for position of this particle is 6t minus t squared minus 4. And we want the position of the particle at time 5. So now we can just plug straight in s of 5, 6 times 5 minus 5 squared minus 4. So that's 30 minus 25 minus 4. So it's 1. And we know the position of the particle at time 5 is 1. Well, let's go and have a look at that. Now, if this is the velocity curve, recall that the antiderivative of this, we can see here we can see that the velocity is 0 here. So the derivative of position is 0 there. So we know that we have, if you recall, we have a local max there because velocity goes from positive to negative. So we know that the curve should look like that. Oh yes, it's an upside down parabola, right? Let's look at this. 6t minus t squared minus 4 is an upside down parabola. So it looks like that, but we don't know how far up or down it is, or do we? We do know that s of 2 equals 4. So s of 2 equals 4, which is right here. So I think we can actually, now we know that, it's not surprising that we can find its position elsewhere. So let's actually superimpose this function there. There's the actual one, right? So I graphed 6t minus t squared minus 4. And looking at that, can I confirm that the position at time 5 is here? And indeed, I know I've got velocity up the y-axis, but I could reuse that scale and just pretend that it's position for a minute, and I get that s of 5 equals 1. So we have that the particle is at x equals 1, remember, because it's moving along back and forth along the x-axis when t equals 5. So this is not the blue curve is not the motion of the particle, right? That just records its position at any given time. You still have to imagine this particle moving back and forth along the x-axis. We are now going to do the same problem, but this time using definite integrals. So before we do that, let's recall the displacement formula, which is really the fundamental theorem of calculus part 2 in disguise. And let's just rearrange that. So I'm going to solve for s of b. So s of b, if I just add s of a to both sides, s of b is just s of a. So the position at time b is the position of the particle at time a plus the area under the velocity curve. Now, why is that? Why do I like this formula so much? Because what that means is if this is the velocity curve or any derivative curve, and you are interested in the position or the value of the function of time b, but you know the value of the function at time a, then doesn't it make sense to take the value of the function s of a and just add the area under the curve, denoted by the definite integral, to find the position at time b? So I kind of like that, just makes intuitive sense. So here's the problem again, and now we're just going to apply this formula. So we want s of b, we want s of 5, and according to this we should do s of 2, because our a is 2, that's where we know the position of this particle at, and then we want to add the accumulation under the velocity function, i.e. the area under the velocity function, from 2 to 5. And we're getting good at this now, so that's 4. I mean, the antiderivative, we're pros at this, from 2 to 5. Notice we don't need a plus c because we're using definite integral. And that would be 4 plus, if we plug 5 into that, we will get 30 minus 25, which is 5. And then if we subtract from that whatever we get when we plug 2, we will get 8. And so 4 plus negative 3, which equals 1, as we got in the previous example. But this one is a little more elegant, this method. So before we practice one last problem, let's just summarize the formulas thus far and add one more that you should have come across in a previous video. So the displacement of the particle over the time interval AB is given by this quantity, this definite integral. The distance traveled over that time interval is given by this formula with the modification of the absolute value. The position of the particle at time b, knowing its position at time a, is given by this expression. And then the last formula I'd like to use at least once in this video is the average velocity over the interval AB is given by 1 over b minus a times the definite integral of the velocity from a to b. And I will link to that video in the description. For the last practice problem, we're going to take the 2011 AP Calc exam question number 1. You're allowed to use a calculator for this question. So we're going to move through this pretty quickly, and I'll be showing you the calculator calculator entries that you should be making. So I've modified part A. This is the only part that's modified. So find the displacement of the particle from t equals 0 to t equals 6. Notice that it's good we're using the calculator because that velocity function, you would not be able to find the antiderivative of that by hand. So here's the displacement formula from 0 to 6, and this is what you would type into the TI-84. You can't see it there, but because I couldn't include the whole screen, but of course there's a dx right there. And you can, for your answer, you should round to 3 decimal places, but you can either write it as I've shown it here. You can just write v of t in there. You do not have to write the whole expression out, but you could also write it out as shown here. And that would work. Either would be acceptable. If the velocity function is very cumbersome, it's just easier to write what's shown in in yellow. All right, and the other next question, find the average velocity of the particle over that time period. And so we have, here's the formula for the average velocity, 1 over 6 minus 0 times the quantity we just worked out in part A. So in fact, all I did is take that and divide it by 6 to get the answer of 1.949. But again, you must make it clear that you're dividing by 6 in this case. So 2 more parts to do for this problem. Let's just call up all the relevant information. Notice that x of 0 equals 2 means that the position of the particle at time 0 is 2. I'm sure that's going to come into play soon. So here's part C. Find the total distance, and we know that that's the formula. And if we put this into our calculator, we get 12.573. Now, oh, I forgot to mention, you must be in radian mode when you're dealing with trigonometric functions. So if your answers were not matching from before, that's maybe because you're in the wrong mode. So the distance traveled is this, 12.573 units. And the last part's kind of an interesting, bit more involved, because it wants the position of the particle at the time the particle changes direction. We don't actually know when that happens. I mean, we could set this equal to 0, but you would have a tough time solving that. And when you're in the calculator section, you should never be doing much by hand. So we're going to find when the velocity is 0 using the calculator. And first of all, you would want to type it into y equals. And then you would want to graph it. So this is the window that I chose. My x min is 0, my x max is 6, because that's the time interval. And you might have to play around with the other values to get a graph that looks nice like this. And now we are trying to find when the velocity is 0. So we're trying to find the coordinates of that point. And to do that, you have to use the calc menu. So hit the calc button and choose 2, 0 to find the 0. And it's going to ask you, it's going to say left bound question mark, and you're going to have to make sure that you enter the cursor just to the left of the 0, and then it'll say right bound, and you'll do it to the right. And then it says guess and hit enter again, and that will get you that x-intercept, that 0 is 5.196. So let me just, let me erase that and then show you the next. Okay, so that's the calculation that we have to work out. So to find the position at this time, 5.196, we're going to do 2. Well, where is that from? That's the position when time was 0, plus that quantity. And if you do that, you get 14.135 is the position of the particle at that time. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.